Now let's know about the TCP/IP security and the tools used for TCP/IP security. Let's have a look again at the header of the IP protocol. This is simply the header of the IP protocol. Let's focus on the field that is called protocol inside this header. This field can take the values either 1 or 6 or 17. If the protocol field is 1, then the protocol forming this packet is the ICMP protocol. If it is 6, then the protocol forming this packet at the upper layer is the TCP protocol. If it is 7, then the protocol forming this packet at the upper layer is the UDP protocol. So you can either have in your network 1, 6 or 17 for ICMP, TCP or UDP consequently. So you have some fields to suspect inside this header. The version field. Why would you have on your network a packet that has in the version field of the IP header the number that is not equal to 4? Any number that is not equal to 4. This means that this header is not IP version 4. Why would you have it on your network? You may think of IP version 6, but IP version 6 is a completely different version of and completely different header. So it would be 128 bits IP address, for example. So if it is not equal to 4, discard this packet. If the length field is more than 5 and there are no options in this header, so this length field is not representing the actual size of this packet header, so it should be discarded. The TTL, the time to live, if it is something like 10 or less, so this packet has been passing so long time over the internet. Why would you have such packet on your network? It may be a lost packet. It has been alive for a long time over the internet without reaching the destination. Maybe it is malicious. Maybe it is an attack. Again, why would you have a packet that is not TCP or UDP or ICMP according to the protocol field in the IP header? Why would you have it on your network? If it is not 1 or 6 or 17, then discard this packet from the protocol field of it. Now think stateful. Think about fragmentation. Why do we need fragmentation? Because sometimes the MTU, the maximum transmission unit, of the sending network is greater than the MTU of the receiving network. So we need to fragment the packet, to divide it into fragments, so that the MTU of the receiving network is fixed and is suited to this packet. To do this fragmentation, you have two fields, the ID and the offset. Different fragments should have the same ID field. Different fragments should have sequence of offset fields that tells the sequence of these fragments. So what if the last fragment of this packet is never sent? The router of the network receiving these packets will keep storing fragments and more fragments till it is overflow. That's maybe what the attacker is trying to do. What if overlapping offset numbers are sent? 1, then 2, then 4, then 1 again, which means that the offset numbers or the fragmentation offset numbers are not telling a sequence of fragments. This means that it wants the router to discard all the fragments it is receiving because it will never be able to assemble once more the fragments of the original packet. About subnetting, consider who are on the same subnet with each other. One subnet is like the virtual LAN. One subnet is one broadcast domain. One subnet should convey the people talking to each other much more than people on other subnets. So consider who are on the same subnet. Do not put the attacker and the victim on the same subnet. You are making it easier for the attacker by this way. consider netting, network address translation, and using private addressing. Remember that each IP address starting with the number 10, for example, is a private IP address. It cannot be published to the internet with its value. It needs some form of network address translation that uses one real IP to communicate a group of private IP addresses to the internet. This form of communication using the network address translation is more secure than exposing all of the IP addresses of your network to the internet. One subnet is a broadcast domain. It is the same as VLAN. Consider this, and consider that the attacker and the victim should not be on the same broadcast domain by any means. Now let us move to the UDP header. The UDP header is simple. It is just the source port, destination port, message length, and checksum. Why would you use the UDP traffic if you don't have either audio or video traffic in your network? Why would you allow UDP to be there? Is it for the sake of DNS? DNS can be used and can work over TCP. So, is it for the sake of NTP, Network Time Protocol, or for the BOOTP protocol? Consider this. Consider having UDP header from the very beginning on your network. UDP traffic can cause flooding. UDP traffic can overflow your network. The UDP port is the same concept port as the TCP. It is either a trusted port, which is less than 1024 in number, or it is ephemeral port, which is more than 1024. Port numbers less than 1024 is for servers. Port numbers that are ephemeral, that are used more than or greater than the number 1024, are for the ordinary machines that are not servers. Look at the TCP header. We have so many fields of the TCP header. Let's focus here on the flags of the TCP header. Let's recall here that we have FTP working on port number 21, Telnet on port number 23, SMTP port number 25, DNS port number 53, HTTP port number 80. Why would you allow traffic to talk to the HTTP server on a port that is not the port number 80, or DNS server on a port that is that's not the port number 53? Why would you allow this? Why would you allow destination port number in a packet which is greater than 1024 to enter your DMZ zone? Remember that the DMZ zone is composed of servers, so all the port numbers there should be less than 1024. Why would you allow anyone to talk to your server with a port number that is greater than 1024? Let's remember the flags once again: the acknowledgement, the SYN, the reset, the push, the FIN, and the flags that are used in the TCP header. And let's recall that we have three-way handshake between the client and the server at the beginning of the communication. It is used by a SYN packet with the SYN flag put to 1 and a sequence number, for example 100. The server replies with a SYN packet and ACK packet using the number 101. Remember that this acknowledgement 101 is because that the SYN was used with 100, so it is the SYN plus 1. And remember also that the client should acknowledge the server once more with an acknowledgement number 501. Why 501? Because the SYN synchronization number that was sent was 500. These three packets are the three-way handshake at the beginning of any session between two TCP machines. And the 4 arrows at the bottom are the four-way handshake used for finalizing and ending and termination of the TCP communication between two TCP machines. It starts with FIN with a sequence number, and then acknowledgement with an acknowledgement number, then a FIN from the same server with a sequence number, then acknowledgement with an acknowledgement number that equals to the sequence number plus 1. This is the ordinary and the normal three-way handshake and four-way handshake at the beginning and the ending of communication between two TCP machines? Why would you have SYN plus FIN? Why would you have ACK plus FIN? Why would you have SYN plus ACK without a SYN that is preceding it? Why would you have acknowledgement without SYN plus ACK? Why would you have reset with anything else? Why would you have a weird communication of flags inside your network? Why would you have a weird communication of combination of flags that do not follow the normal communication of three-way handshake and four-way handshake? If any of these combinations exist on your network, so this says that you have malicious traffic inside your network. Now, before ending this lecture, we would like to explore a tool that is very useful for the TCP IP traffic, which is called the Engage Packet Builder. Let's here start with the installation of Engage Packet Builder. This Engage Packet Builder is a tool to craft some packets with the values that you like, with whatever values that you like to craft, with whatever headers that you like to set. This Engage Packet Builder is free and can be downloaded from the internet easily. And how it looks like. You can see here that you can set any of the TCP flags with whatever value you like to set. You can set the source IP address, the destination IP address of the packet, the type of service field, the fragmentation fields, the protocol fields, with whatever values that you can like. And you can at the end send the packet with these values that you have set. It can use the TCP, the UDP, the ICMP packets. You can use whatever protocol to craft a packet and choose even the number of packets you want to set or you want to send with this configuration, and send them to whatever destination IP address you would like to set. This is very helpful in understanding the TCP IP protocol headers. Thank you.